Hi, we are Team Echo-2, also known as Echolocation, and we are in charge of living on the lunar surface. Let's introduce the team. My name is Aditya Rajavelu, I'm the systems engineer, and a fun fact about me is that I play the guitar and produce music for my YouTube channel.
Hi, my name is Katie Thiessen, and I'm the integration manager, and a fun fact about me is that I like classical piano.
Hi, my name is JC Eldridge. I'm the design manager for Team Echolocation, and one fun fact about me is that I love structural design.
Hello, my name is Ashmeet Bedi, and I'm the design engineer. A fun fact about me is that I moved to Texas 4 years ago from Virginia.
Hi, I'm Dan Lundquist. I am subtopic manager number 1. A fun fact about me is that I once got launched off a tug-of-war rope because I stood on it with both feet.
Hi, my name is Nurja Patel. I'm the subtopic 1 technician, and a fun fact about me is that I did competition swimming for almost 10 years.
Hi, my name is Sai Ganesh, and for the team, I'm the subtopic manager number 2. And one fun fact about me is that I enjoy playing basketball.
Hey, my name is Joshua. I'm the subtopic 2 technician, and a quick fun fact about me is I like to play basketball.
Hello, my name is Sham Devnath, and I'm the subtopic number 3, Lunar Surface Hazards Manager. And a fun fact about myself is that I'm currently in Alaska presenting a poster on black holes.
My name is Ayan Imran. I'm the subtopic 3 technician. A fun fact about me is I play 5 different sports.
Our Team Echolocation's patch consists of a scholar hat shown at the top of the patch, which represents us scholars and how we were given this amazing opportunity. The echo and bat symbolize our team name, Echolocation, by representing the way bats gather information. The astronaut on the moon represents our team's mission, living on the lunar surface. The stars and rockets represent the technological barriers we will have to overcome in order to accomplish our mission, as well as our union under the United States.
In order to select our subtopics, we first focused on the essentials for sustaining human life away from Earth. We determined that it was essential to offer lunar hazard protection, as well as temperature and pressure mitigation for this reason. With those 2 subtopics selected, we were left with a choice between pilot plants and the launch pad. While a pilot plant on the moon would allow for the industrial processes of products made from in situ material to be quickly tested with ease of access to said material, we determined that it would be more reasonable to invest our time in a launch pad that can transport lunar material back to Earth, where we have more access to industrial production tools. In service of collaboration, all teams made their mission statement clear and systematically asked questions towards and from each team to ensure total mission cohesion. Before each systems engineer meeting, I compiled the research we had done into a short report to concisely present our current progress to the other teams, then reported the feedback and necessary change requirements to my team.
Building a launch pad on the moon presents unique challenges due to the lack of pre-existing infrastructure and the high cost of transporting materials from Earth. Our solution to this is in situ resource utilization, ISRU, which involves harnessing resources already found on the moon rather than relying entirely on Earth-based supplies. Lunar regolith is the fine layer of dust and debris that covers the moon's surface, and its abundance makes for a promising material for ISRU and construction. In addition to being widely available, regolith provides natural protection against cosmic and solar radiation, which is essential for the safety of astronauts in lunar habitats. Because the moon lacks a substantial atmosphere, temperatures can shift dramatically, especially during lunar nights, which last up to 2 Earth weeks. Using regolith can help maintain heat and retain habitable conditions during these prolonged cold periods.
While using regolith in our launch pad has many benefits, as Dane was saying, there are also some drawbacks. Inhaling this regolith can be hazardous for astronaut health, but along with this, there are also specific engineering challenges that arise. When rockets are launched from the moon, the sharp regolith particles are kicked up, and due to the moon's weak atmosphere, the particles don't slow down and can cause damage to equipment. To combat this problem, we have decided to mix lunar regolith with binders or polymers from Earth, such as epoxy or sulfur. Mixing and processing together into a lunar concrete creates a solid, hardening surface that can withstand high temperature and pressure from rocket launches. Additionally, NASA developed an interlocking paver design which locks down 6 degrees of freedom. The pavers, which are polygon or spacer tiles, are arranged into a checkerboard pattern. This enhances stability and minimizes erosion caused by the regolith. If the paver is installed via a robot, then the need for human labor in harsh environments can be reduced, thus reducing the health risk. Through this, regolith can be widely used, mitigating its consequences.
As we analyze the moon's condition, it's been clear that our design would require more detail.
Initially, our design was based on aluminum reinforced with Kevlar, a strong heat-resistant synthetic fiber. But because the aluminum would need to be very thick to protect against radiation, adding unnecessary weight and bulk, we would need something more efficient.
Temperatures on the surface range from 127 degrees Celsius in the sunlight to negative 173 degrees Celsius at night, and there's no atmosphere or pressure to help moderate the internal environment. Therefore, the aluminum Kevlar design lacked any kind of insulation, meaning astronauts would not be protected from these temperature fluctuations. And because of this, we transitioned to a multi-layered design. The Kevlar inner layer in this new design provides flexibility and strength. Next, we have a layer of aerogel insulation, a NASA-used material with one of the lowest known thermal conductivities, just 0.013 watts per Kelvin meter, to slow down heat transfer. After that is a layer of lunar concrete, which acts as both a radiation shield, as Nirja and Dane discussed earlier, and an impact buffer. Studies from the European Space Agency showed that it can block up to 95% of cosmic radiation when compacted. And finally, a Kevlar outer shell protects against micrometeoroids. This new setup balances safety and efficiency while leveraging in-situ materials to reduce launch mass and meet our mission goal of building a long-term lunar base.
To confirm its effectiveness, we use the concept of thermal resistance, calculated by taking the thickness of material, d, and dividing it by thermal conductivity, k. The result, r, tells us how well the material resists heat flow. Higher r means better insulation. Even though aerogel is fragile, robotic assembly can be used to construct these layers efficiently and effectively. This final design offers thermal control, radiation shielding, and physical protection needed to keep astronauts safe and achieve a sustainable base on the moon. In the greenhouse on our lunar base, we use radiation shielding glass from Corning, which blocks gamma and X-ray radiation, while allowing safe visibility into the habitat. This was designed not only to maximize natural sunlight paired with artificial lighting, but also to minimize radiation.
Now let's talk about some of the hazards that the astronauts may face on the lunar surface. Now, due to a lack of significant mass and magnetic field, the lunar surface is susceptible to micrometeoroids and orbital debris, as much as 23,000 per year, and causing radiation up to 200 times that on Earth. Now, during the Apollo missions, the short duration of the flights meant that radiation exposure remained within safe limits, allowing standard spacesuits and the lunar module to provide sufficient protection. A report by NASA scientist Claude Lee at Langley Research Center states that it is essential for radiation levels to be kept as low as reasonably achievable. One way NASA shields from radiation currently is through a physical deflector shield on the ISS. We also researched a NASA-developed spray for textiles with shielding properties and investigated regolith's potential to serve as a radiation shield as noted in the other subtopics reports.
Thanks, Ian. So with these in mind, we began our first design. We started with an aluminum frame combined with a Kevlar outer layer, which was sprayed by the NASA radiation shielding. This is a relatively simple design and is also easily transportable and provides protection from micrometeoroids. However, we soon realized it did not provide enough insulation after discussing with Joshua and Sai. So together we came up with that multi-layer approach that they described, which, thanks to the regolith and the aerogel, also provides radiation shielding. And thanks to the availability of regolith and the light weight of aerogel, it's also very feasible. It also provides strong protection against micrometeoroids thanks to the number of layers, and that also plays into the layer principle when protecting against radiation. The con, however, is that there's a lot more material to transport, which may be more expensive.
Our team's task was to design a surface habitat to support 8 crew members on the surface of the moon for 10 months, with various scientific facilities on board to analyze lunar conditions. This will allow for innovative new research into uses for lunar in situ material, as well as pave the way for future missions on Mars.
In service of this goal, we researched and considered a variety of possible solutions for critical points of the base. For communication, we considered 3 different technologies: lunar link, radio communication, and satellite networks. We found that while radio communication was rather inexpensive due to its widespread use, having an unreliable direct line of sight to the moon increases the difficulty of such communication. While a satellite network around the moon may solve this problem, the technology will be very costly to set up and is therefore not practically viable, outweighing its potential benefit. Eventually, we decided on using Lunarlink to maintain parity with most other teams on the Artemis mission. For the greenhouse, our source of food, we opted for cylindrical shape to reduce material used and decided on a compromise between a solid material and a full glass exterior, using a framed glass design with grow lights to maximize light exposure while maintaining the structural stability and viability of the design. One restriction of the surface habitat is its composition of mostly lunar regolith, requiring the extra tools necessary to mix regolith with polymers to neutralize its dangerous effects, increasing overall mission mass. However, with its heavy use of in-situ resources, the habitat greatly decreases mission mass as well, while maintaining the comfort of the astronauts within the base.
This will be the first building incoming crew members will enter when going into the base. The maintenance building incorporates an airlock module, including a decontamination system and a pressurization system, to combat the risk the lunar atmosphere and dust brings in. As for the lunar dust, it is electrostatically charged and would stick to basically everything. It'd be really hard to get off. So that is where the decontamination system is crucial. Past the airlock module, you have the maintenance building. So as you can see, we have plenty of storage units. Specifically, we have rover batteries, and we have the rechargeable platform that the other teams will need, and the rover too. We have an air ventilation system too. This is pretty much the maintenance building here. And to the left of it, you'll see our laboratory building. This laboratory portrays a biomedical station for evaluation of the crew members and a geological station for testing and evaluating samples on the second floor. As you can see on the first floor, we have a little bit of a lab, along with storage units and books, and that is the laboratory building. The designated hallways make sure to securely connect each building to each other, and also carry pipelines and air ventilation systems throughout the building. Going through the walkways and into the greenhouse, for our second power source that the base can be solely reliant on, we have solar panels, which actually was made to combat one of the challenges we faced in our area. Our area has days where the sun is consistently at the horizon and very long nights.
Throughout the process of designing the base, we went through many iterations of the different items and buildings. We decided to remove the glass from the rover maintenance building and swap it for regolith to reduce the amount of glass we use, reducing the overall cost.
The solar panels ensure getting an abundance of sunlight when the sun is consistently at the horizon, and properly made to be adjusted in angle if desired. This energy source provides security for the base, good energy to go off of, and energy that can be stored away for later or in long nights.
Now, the building in the corner, the Essentials building, includes a full living space to accommodate 8 people. There are 8 rooms that each include a bed, a desk, a chair, and a chest to store their personal belongings, minimizing the space and materials by eliminating the need for a full-on closet. There are 2 full bathrooms down the hall, each with a sink, a cabinet, a toilet, and a shower. Now going upstairs from the living area, we have a gym that allows for both muscular and endurance training, with 4 treadmills and 4 squat racks. Going up another small set of stairs will take us to the kitchen/dining hall, with a kitchen and 2 full dining tables. This layout enables crew members to eat, sleep, and work out all in one building without the need for much travel. All appliances that need water, including the bathroom appliances and the kitchen appliances, are connected to the main pipes that run throughout the whole base. The roof of the Essentials building has solar panels on it that curve with the roof, letting it capture more sunlight from the horizon. This captured energy is stored in multiple solar generators connected to the solar panels. These power stations can be disconnected and taken elsewhere, allowing for easily available power anywhere in the base. Additionally, right across the Essentials room through a small walkway is the comms room, with satellite dishes mounted on top of it. It allows for easy communication using LunarLink. After receiving rover dimensions from both Golf and Delta, we scaled down our entire base to accommodate them, which also led to the addition of MMRTG batteries at the maintenance center. Afterwards, we decided to remove the kitchen and dining hall above the living area to localize all essential buildings on one side of the base. Afterwards, we decided to move the kitchen and dining hall above the living area to localize all essential buildings on one side of the base.
When designing our lunar base, it was important to keep in mind that we were the main support for many surface operations. To this end, we made sure our maintenance center was able to accommodate the dimensions of the rovers built by both Team Delta and Golf, including a charging station for Team Delta rovers and spare RTG batteries for Team Golf rovers. Additionally, it was important to utilize in-situ materials, such as regolith, to reduce the material load required to be transported to the lunar surface due to the large dimensions of our lunar habitat.
It was also important to coordinate the materials and technologies our team would be using with other teams. For example, it was determined that every team except Foxtrot would be using LunarLink in order to communicate with other portions of the mission.
Our team had a lot of fun and greatly enjoyed collaborating with many other teams on such a wonderful experience.